In this screencast, we are going to talk about dehydration reactions, and we are also going to talk about oxidation reactions, as well as some uses for common alcohols. Now, alcohols can undergo a lot of different reactions, but we're only really going to look at two right now. One is alcohol dehydration, which we're going to look at first, and then alcohol oxidation. In an alcohol dehydration reaction, water is removed from the alcohol, and that's shown here in blue, right? And we can see the water here. This is a temperature dependent reaction, so the temperature matters. If it's at 180 degrees, it's going to form an alkene. If it's at 140 degrees, the major product's an ether, and we're going to focus more on that in a few slides. So when these elements of the water molecule are removed from a single alcohol, right, we form that double bond. And so I want us to look at a specific example. So let's take CH3, CH, right, CH3OH. And so if you had a problem like this, it would look like, it would be set up like this, and it would say, okay, you need to predict the product here. And so you would look and you would say, okay, I'm starting with this alcohol functional group. We are reacting it with a strong acid. This is sulfuric acid. And we are going to form a double bond. And so when you do this, you're going to remove the OH here and then one hydrogen from one of the two adjacent carbons. And this happens to be symmetric, so we can remove it from either one. And when we do that, we end up with a double bond. We also produce water. Now, maybe the burning question in your heart is, Dr. Pierce, what if it's not a symmetric alcohol? Okay, and so, for example, let's say you have CH3, CH2, CH, OH, CH3. And I want you to notice it's not the same on both sides of the alcohol. One has a methyl group and one has an ethyl group here. So in this case, we form two products. One product's formed by removing a hydrogen from this carbon, and one product is formed by removing a hydrogen from this carbon. So I'm going to draw these out, and then we're going to talk about which one is the major product and how to identify the major product. Okay, so when we look at this, right, we formed 2-butene, which is right here, and 1-butene, which is right here. 2-butene is the major product. That means we form the most of that. 1-butene is the minor product. That means we form the least of that. And so the question is, why? Well, 2-butene has two carbon groups on the double bond, while 1-butene only has one carbon group on the double bond. And I'm going to highlight that for you so that you can see it. So when we look at it, right, here's the carbon of the double bond, and there's the carbon of the double bond. And then here's the carbon of the double bond, and here's the carbon of the double bond. And what I mean by that is by having two R groups attached to the carbons of the double bond is that the carbon here has an R group and the carbon here has an R group. Well, over here, when we look at 1-butene, we only end up with one R group off of this double bond right here. And so it makes it less stable, so that becomes our minor product. So we can make a generalization here. The more carbon groups attached to the carbon of a double bond, the more stable the product is, and it's more likely to form. And so when we talk about this, you can have a carbon-carbon double bond with 4 R groups, and that would be the most stable, right? And then you can have a carbon-carbon double bond with 3 R groups, and that would be less stable than the most stable. And then you can have a carbon-carbon double bond with 2 R groups, and this can either be cis or trans. Okay. And then you can have a carbon-carbon double bond with just 1 R group, and this is the least stable. So when you're trying to pick the major product, you have to look at how many R groups or carbon groups are attached to the carbon of the double bond. Now, this particular reaction is really important in the human body. We see it in the citric acid cycle, where citrate is dehydrated by an enzyme, and so the hydroxyl group here and the proton here go to form the water, and then a double bond is formed here. Now, one of the things that is interesting, or at least to me, is that the dehydration of citrate, 2-propanol, which we looked at the previous slide, and 2-butanol, all involve exactly the same changes in bonding. All of them remove a hydrogen from one carbon and an OH from the adjacent carbon to form water, and then a double bond. So one of the reasons we study organic chemistry is because these patterns with these functional groups, particularly with reactivity, can be applied to larger problems like what we see in the citric acid cycle. Now, as I mentioned on the first slide, we can also have alcohol dehydration when the elements of water are removed from 2 alcohol molecules. So, for example, if we had ROH, which is an alcohol, plus HOR, which is another alcohol, and they react in sulfuric acid at 140 degrees Celsius. So this is a lower temperature. It's not that 180. What you're going to see is that the OH here and the H here will form water. And then, and I'm going to make this an R prime here. And so then you would have RO R prime plus water that's formed. And so this is an ether. And we use R just to say, hey, look, that's a hydrocarbon side chain, and that the 2 R's can be the same or they can be different from each other. So if we looked at a specific example where we reacted 2 molecules of alcohol or ethyl alcohol, with a H2SO4 at 140 degrees, we would see that we would form CH3, CH2, O, CH2, CH3. When we look at this, we have the CH2, CH3 here, and then we have the OCH2, CH3 here, and then this component and this component are what form water. And so we can predict the products when we see these two alcohols reacting together in an acid at 140 degrees Celsius. Now, this reaction is an example of a dehydration synthesis where two molecules here are joined and a new functional group is generated by that removal of the water molecule. Dehydration synthesis is really important in living organisms because it's part of the formation of carbohydrates, fats, and proteins. And so we'll study this more later. I mentioned the second type of reaction that we're going to look at are oxidation reactions. And oxidation reactions occur when a molecule gains an oxygen or loses a hydrogen atom. And when we talk about this, it can also gain when it says gain an oxygen atom, I really like to think about that as gain a linkage or gain a bond to an oxygen atom. So for example, in this example here, we have an alcohol group here, and we're reacting with a oxidizing agent. And these can be a couple different things. They can be potassium chromate or potassium permanganate are really good examples, but it's generically shown as an O. And then what you're going to see here when we have an alcohol is we're either going to form the aldehyde or ketone functional group. Notice that we have just one bond between carbon and oxygen and one bond between like the carbon hydrogen here and the oxygen hydrogen here. And we reduce the number of carbon hydrogen bonds. Okay, so this carbon is going to lose a hydrogen. And then we gain a carbon-oxygen linkage. And so that's the indication that an oxidation reaction occurs. The symbol O here is given for oxidation agents. You're either going to see it as an O like this. Sometimes you're going to see it as an O in brackets. But either way, you know that that's your symbol for oxidation is occurring. Now, we learned in the previous screencast that there are 3 classifications for alcohols, and I said those react differently. And so we're going to see how the 3 classes of alcohols react differently towards oxidizing agents in this screencast. So one of the things that we're going to look at first are primary alcohol oxidation. The immediate product of the oxidation of primary alcohols is an aldehyde, which is shown here. However, aldehydes are then readily oxidized by the exact same oxidation reagent in the vessel to give a carboxylic acid here. So the oxidation of a primary alcohol normally results in the corresponding carboxylic acid as the product. Now, you can go through a separation where you can separate this out by boiling because these have a lower boiling point. Aldehydes have a lower boiling point than carboxylic acids because they don't have as much hydrogen bonding. So that's a way to separate them, but what we're going to say is, hey, look, they go all the way over here to carboxylic acids. I want to show you what this reaction would look like when you did it. So for example, when we look here, we're taking ethanol, which is one of those primary alcohols, and we are taking it through an oxidation reaction. When we do this, right, we start here with this orange tube on the left, and that contains the oxidizing agent, which in this case is potassium chromate. And then we have the ethanol here. So what happens is this oxidizing agent is poured into the ethanol and immediately this green color forms. And that's the indication that the chromium itself is reduced and then that ethanol is oxidized. This used to be used in breathalyzer tests. It's quantitative, so people would breathe into a tube that was coated with the potassium chromate, and however many the length of how the tube changed color would indicate how much alcohol had been consumed. So that's I think it's kind of a really neat visual example. Now, the next thing we're going to do is look at secondary alcohols, which are shown here, reacting as well, but we see this here as well. So secondary alcohols are oxidized to ketones in the exact same way that primary alcohols are oxidized to aldehydes. So there's a hydrogen removed from the oxygen and a hydrogen removed from the carbon that's attached to the oxygen, and a double bond forms. Now, unlike aldehydes, ketones don't oxidize any further, so this is a really great way to prepare ketones, because this is the product that you're going to get. Now, when we look at tertiary alcohols do not have any hydrogens on that carbon. So there are no hydrogens on the carbon, so they can't go through oxidation. And so if we were to have this reaction here, we would say, oh, nope, it doesn't work. And so we get no reaction here. So tertiary alcohols do not react in oxidation reactions. Now, just like we looked at a map for reactions with alkenes, this is a really nice map for reactions with alcohols. We start here with our alcohol, and if we react it with sulfuric acid, it'll undergo a dehydration reaction. If it's at 140 degrees, the alcohols will react with each other and form an ether. If it's at 180 degrees, then we will form an alkene. Alcohols will also undergo oxidation with either potassium chromate or potassium permanganate. And if it's primary, you'll form an aldehyde, then a carboxylic acid. If it's secondary, you'll form a ketone. And if it's tertiary, there won't be any reaction. Now, one of the things that we do in chemistry is when we look at reactions, we can have multi-step reactions. And alcohols are really important organic compounds, not just for their commercial applications, but because they can be converted by chemical reactions into a large variety of other useful products. Most alcohols don't occur naturally in commercial quantities, and so we prepare these, or we synthesize these from alkenes through multi-step reactions. It's very common in both the laboratory and industrial setting for preparations to involve a sequence like you see here. And so this is what we talk about when we say a multi-step reaction, where, for example, we start with commercial ethene, and then we make vinyl chloride, and then we use the vinyl chloride in a polymerization reaction to form polyvinyl chloride here. Nature also uses this method of multi-step reactions to carry out processes that are really essential to life. So the glycolysis pathway, for example, has a set of 10 reactions, and this is how we process glucose for energy production. So let's look at an example of a multi-step reaction problem. So in this multi-step reaction problem, it says the following conversion requires more than one step. Show the reaction, reagents, and intermediate structures necessary to carry out the synthesis. So when we look at this, right, what we have here is the reactant here and the product here. And we want to look and see how these change as far as their functional groups are concerned. And so when we look at this, we say, hey, look, we have a double bond here, and that tells me it's an alkene. And over here, we have a ketone functional group. Now, I have put our two reaction maps here that we've used so far. And so when we look at our two reaction maps, we see here with the alkene that we've learned how to make an alkane, a haloalkane, an alcohol, and then another haloalkane over here. And then I want you to notice with our alcohol here, this is the only way we've learned how to make a ketone. So you need to use your reaction maps to figure out how to get from one to the other. It's kind of like a puzzle. So if we think about puzzle pieces, you're just putting the different puzzle pieces together. If this is your starting material to get to this. There are two ways to do this. You can either work forward or you can work backwards, and you can do whichever one is the most comfortable. So what I'm going to do is I am going to work forwards, where I am going to do this step to turn an alkene into an alcohol. And then when I have an alcohol, I'm going to go through and do this step to turn it into a ketone. So when I think about this, right, and I think about my alkene, I'm starting here with this molecule, and then I know it can undergo a hydration reaction where it reacts with water and sulfuric acid and forms an alcohol right here. So we've done this part of the process, and now we're going to come over here to our alcohol, and it can undergo oxidation. This is a secondary alcohol to form a ketone. And so we're going to come here and we're going to say, hey, look, that's going to undergo oxidation. And now that is our oxidation product. So this is a way where we can string many different reactions together and show a series of reactions to form a product. This means, for example, if we don't have any alcohols to make this ketone, we could then start with the double bond. So if we have the double bond in the stockroom, that's what we can use. Now I want to end the screencast by talking about a few important alcohols. Methyl alcohol, or which is also known as methanol, is shown here with this structural formula. It's also known as, historically, wood alcohol. Its uses include, it's used as a solvent, formaldehyde. It makes formaldehyde, which is used as an industrial starting material for plastic production. So a lot of times it's used in a multi-step synthesis for this. It's also used as fuel in, for example, Indy-style racing cars. It is highly toxic and causes blindness or death if it's taken internally. So this methanol is a byproduct in the 1930s during Prohibition, when people were trying to make their own alcohol. That was the product that made people go blind. Ethanol or ethyl alcohol is also called grain alcohol. It's produced commercially from ethylene, which is a carbon-carbon double bond, or through biologically using yeast fermentation of carbohydrates. It's used as a solvent. It's also in alcoholic beverages, and it's moderately toxic. 2-propanol is also known as isopropyl alcohol. This is used as rubbing alcohol. So when you go into the grocery store and you buy rubbing alcohol, you're using isopropyl alcohol. Another alcohol that's interesting is 1,2,3-propane-triol, which is known as glycerin or glycerol. This is used as a moisturizing agent in food and tobacco products. It's also used as a soothing agent in soaps, which I think is kind of interesting. We also have 1-butanol, which is a solvent. It's also found in hydraulic fluid. 1,2-ethane-diol, which is known as ethylene glycol, which is found as antifreeze in your car. It's also used to make polyester. Then we have propylene glycol, which is used as a moisturizer in lotions and foods, and also automobile antifreeze. And then finally, we have menthol here, which is an alcohol that's used in cough drops and shaving lotion and mentholated tobacco. So these are a few important alcohols that you will kind of see as you walk through the grocery store or read the back of labels, food labels. And so I just wanted to highlight those briefly. So in this screencast, we've learned about two important reactions that alcohols go through: dehydration and oxidation, and then we talked about multi-step synthesis, or how to put different synthetic steps together that we've learned about, and then we highlighted some important alcohols. If you have any questions, as always, feel free to stop by my office.